Hello and welcome to this module on support vector machines. So, we have been looking at a variety of classifiers so far, and one of the things, let us just look at a linear classifier. So, one of the things is, if I have data points that are even perfectly separable, right, here is a class and here is another class, you can see that they are very clearly separated, but when I train a linear classifier, it is not entirely clear which of these many possible lines that could separate the data, right, would your classifier end up learning. Right? There are many different lines that could separate the data, and we are not sure what your classifier would end up learning. Right. So, support vector machines initially were born out of a need to answer this question. Right. Among all of these different lines, right, or all of these different decision surfaces that you could use for separating the data given to you, which of those is the best decision surface? Right. So, among all those alternatives, which you think should be the best decision surface? Right. So, one answer to this question, right, is to define an optimal separating hyperplane, right, as the surface such that the nearest data point to the surface is as far away as possible, right, among all such surfaces. So, here is a separating line, right, and the nearest data point to that is that or that or that. Right. So, if you think about it, so the nearest data point cannot belong to just one class. Right. So, I could draw a line like this, right, but then that would mean that I am reducing the distance of the data point to the separating surface, right, or if I go this way, again I will be reducing the distance of the data point to the surface in one class or the other. When I say that you are maximizing the distance of the closest data point to the separating hyperplane, that essentially means that the closest data point from either class is at the same distance away from the hyperplane. Right. So, this distance would be the same as this distance, would be the same as this distance, right, and this right. So, this distance of the closest data point to the separating surface is known as the margin. It is known as the margin of the classifier. Right. Which will denote by m. So, the goal of finding a optimal separating hyperplane is essentially to find a classifier such that this margin m is as large as possible. Okay. So, let us step back and think about what such a line means. Right. You know, in all linear classifiers we have seen so far. So, we know that we are going to say something like so, y is beta naught plus beta transpose x. For convenience sake, here I will write it as x transpose beta, since we are taking inner product, that is fine. So, a line like this would essentially be obtained by setting this beta naught plus x transpose beta equal to 0. So, all the data points on this line, right, are those data points for which beta naught plus x transpose beta evaluates to 0. So, that is the equation of the line here. Okay. So, if it is negative, beta naught plus beta transpose x is less than 0. So, we are going to say that x is of class minus 1, right, and if beta naught plus beta transpose x is greater than 0, we will say that it is class plus 1. So, remember that. So, we will be using some kind of encoding for the class, right. The class could be does not buy a computer or buys a computer, right, is sick, is healthy. I mean, the classes could mean many different things, right, but numerically we are going to be assigning some encoding for the class, and in this case I choose to use minus 1 and plus 1 as the encoding. There is a reason for that, as we will see shortly, right. So, if beta naught plus beta transpose x is less than 0, right, I say it is class minus 1, but in this case what do I really want? I do not want it to be just less than 0, right, I want it to be at least m away from the hyperplane, right. I want it to be m away from the line beta naught plus beta transpose x equal to 0, right. Yeah, so I might use x transpose and beta transpose x interchangeably at points, but as you know they are inner products, so it is fine, right. So, what I really want is right. So, if y I is plus 1, I want beta naught plus x I transpose beta to be greater than m, right. What happens if y I is minus 1? I really want it to be at least m away in that case as well, right. But then we know that beta naught plus x I transpose beta would be negative, right, when the class is minus 1. So, what I do is I essentially just multiply it by the actual class variable, and I want this whole distance, right, because if y I is plus 1, I would like this also to be plus the positive, and I want it to be at least m away from the hyperplane, and y I is minus 1, this is going to be negative. So, the product is going to be positive, and I want that to be at least m away from the hyperplane. Right. So, this is the constraint that we want to satisfy, right. And what is our goal? If you remember, our goal is to make sure that this m is as large as possible, right. So, what we will do is we will say, okay, maximize m, okay, beta naught and beta subject to right. So, I am going to maximize the margin m, okay, over beta naught and beta subject to the constraints that y I times x I transpose beta plus beta naught is greater than or equal to m for every data point in my training data. Okay. So, this can be done assuming that all the data is nicely separated, right. So, I can actually draw a linear surface that separates the data. So, if I can draw a linear surface that separates the data, then I can come up with at least one surface that satisfies this constraints for some value of m, right, and essentially I have to find the value of m that is maximum here. But one thing, if you look at this equation or the constraint that we have written, So, I can arbitrarily increase the value of beta, right, and make this value as large as I want, right. So, I need to have some constraint on beta as well. So, what we will do is we will constrain the norm of beta to be equal to 1, right. So, we will not look at all possible weights beta naught and beta, okay. We will only look at those weights in such that the size of beta is constrained to be 1. So, the norm of beta is you could take the Euclidean norm of beta, I am saying that the Euclidean norm of beta should be 1. Okay. So, I hope the formulation of the optimization problem so far is clear. So, it is essentially saying that I want all my data points to be at least a distance m away from the hyperplane, and subject to that constraint and subject to my beta being norm 1, I want to maximize the margin. Okay. So, this is a pretty irksome constraint. So, we can try to get rid of it by changing the other inequality constraints to by normalizing them with beta, right. So, this again allows me to achieve the same effect of not getting a high value for m just by increasing the size of beta, because I am dividing by the size of beta, right. So, that achieves the same constraint. And again essentially write it like that. So, one thing that we should note here is that if a specific beta satisfies these constraints, right, any positively scaled version of beta would also satisfy the constraints, right. I can just multiply it by some positive number. Okay. If it was originally all for all the xi's, it was giving me negative values larger than m or minus m, or positive values larger than m, just multiplying it by a positive quantity will not change anything, right. It will still give me negative values that are lesser than minus m or positive values that are greater than m. Okay. Therefore, I can essentially choose a specific value for beta, right, such that this evaluates to 1, right. So, I set So, I set norm beta equal to 1 by m, right. So, that this constraint becomes yi xi transpose beta is greater than or equal to 1, subject to the constraint that you are finding the smallest such beta. Right. So, this optimization problem then becomes this optimization problem of maximizing the margin now essentially becomes the problem of finding the smallest beta such that these conditions are satisfied. Right. So, this essentially means that my margin here is going to be 1 over now beta. So, to make it mathematically more convenient, I am going to minimize a quadratic form of that. So, essentially I will be minimizing the square of beta, since it is a norm anyway. So, this will be positive to begin with. So, I can minimize the square, that is not a problem, right. And so, that is my final optimization problem, right. So, this is the final optimization problem, where I am saying that. So, together with these constraints, right, I kind of define a slab around the separating hyperplane. I define a slab around the separating hyperplane of width 1 by beta, right. So, making sure that there are no data points within this region, right. So, I am trying to now maximize the width of this region, so that there are no data points in that region. That is essentially the idea behind this optimization problem. Right. Okay. So, this defines the basic optimization problem in the case of support vector machines, right. So, in the next module we will look at how do you go about setting up a solution for this optimization problem.